Okay, let's go ahead and spend the last part talking about salts. By salts, I'm actually referring to ionic compounds. And table salt, what you normally think of as salt, is just one of many, many ionic compounds that we also call salts. All ionic compounds, by definition, are going to have at least one cation and at least one anion. And, they're sticking together by the opposites of charge. Now, many ionic compounds have multiple cations and multiple anions. We're going to kind of ignore those. Leave those over to the geologists. Things get really complicated. We're just going to look at the ones that have one cation or one anion. And we're going to go a little bit more in depth. What we deal with this individual ones, the ones that's one cation, one anion, the same story goes for the multi-cations and multi-anions. But we're going to deal with ones that have one type of, not just one individual, but one type of anion and one type of cation. And if you've got the nice simple ones, once again, not going to be trying to name the ones that have all kinds of weird stuff. Those usually get some mineral name. When we're naming them, we're going to name them by the name of the cation and the name of the anion. And if you're trying to figure out which one's which, the cation is probably going to be a metal. There's a couple of cases where it's a non-metal, but apart from ammonium, which is used in fertilizer and things like that, it's about the only time you're going to see it. And then the anion is almost certainly going to be a non-metal. There's a couple of really weird cases like hydrogen as an anion. Those tend to be psychoreactive though. And so we're not going to kind of deal with them too much. When we're naming them, it's going to be fairly straightforward. The cation just keeps its name. So if I have lithium for my cation, then my salt's name is going to be lithium and then whatever the anion is. Now, the anion is going to have its name changed. It's going to drop the last syllable, and you're going to replace it with "ide." So if it's a chlorine, I would have chloride. So lithium chloride. Yay. Now, with our salts, we're also going to want to look at not just how to name them, but how to create their chemical formulas, what we call an empirical formula in this case. Now, the reason we want to do this is that we want to know what elements are in there, and we'd like to be able to write it a little bit easier than writing out the whole name of the thing. If we could just use the elemental symbols, that would be awesome. But we also want to look at the ratio, because remember, all compounds, and all of our salts are going to be compounds. They have two different elements in it, at least. All of our salts are going to have a ratio, a nice fixed ratio of elements in it. So we want to know what that ratio is. And the convenient thing about ionic compounds, convenient thing about these salts, is that generally speaking, you only get one fixed ratio per two elements. So it's fairly straightforward. So the way we're going to do is we're going to get our formula, and we're going to show how to actually do these and get the information out. But we're going to start out by writing the symbol of the cation. Now, obviously, if you've got multiple, then you would have multiple symbols here. But you're going to write the symbol of the cation first. And then below it, well, not really below, more of down and to the right, in subscript, you're going to put a number, and that number denotes how many of that cation is in the ratio. So if it's a 3-to-2 ratio, then I'd put a 3. If it's a 1-to-1, I wouldn't actually put a 1, but I'll get to what we do with 1s here in a second. Then you write the anion, and subscript on the right-hand side, you also put its number for the ratio. This is what we call the formula unit, basically the smallest whole number ratio of everything together. Now, if they're a 3 and a 2, you just write the 3 and a 2. If they're a 1, though, 1s are going to be assumed. It's kind of like music where, we don't tell you everything if we don't have to. So obviously there's at least one chlorine in sodium chloride. Otherwise, why would you call it sodium chloride? You'd call it sodium something else. So I don't actually have to tell you there's a 1. So you're going to have symbol, you're going to have the number. If that number is a 1, you just omit the 1. And then you have the next symbol. No space, nothing, no punctuation, nothing else. You know that there are two different symbols because you have got a capital letter. So if I look at the magnesium chloride, sorry, not magnesium chloride, magnesium nitride. I'm looking at both of them at the same time. Magnesium nitride, I know the magnesium starts with the M because the M is capital. The G is lowercase, so that's modifying the M. So it's magnesium and not, well, there's nothing that actually is just M, but you get the idea. If I look at the sodium chloride, I know that it's Na. is sodium. The A is lowercase, so it's modifying the N. So it's not nitrogen and something else. It's sodium. And then the Cl, it's not carbon and then, once again, I don't think there's actually just a straight L, but it's not C and then an L. I know the L modifies the C because the L is lowercase. No punctuation. And this is why we are so strict on those chemical symbols with the upper and then lowercase motif. Now, if we want to do this, we are going to have to know what the smallest whole number ratio is, but the name doesn't include it. Sodium chloride just tells me what's in there, but in order to do the formula, I need to know what it is. Now, let's go for something nice and straightforward. Let's go for magnesium nitride, which is, you know, a little bit more complicated. The way we're going to sort this out is we're going to take the total charge of all of our cations, and we have to make sure that they are equal to the total charge of all of our anions. Obviously, if you've got multiple types of cations, this is going to be much more difficult, but we're not going to deal with that. We're assuming you got one type of cation and one type of anion. So magnesium, I look on the periodic table, and I'm going to figure out it has a +2 charge. It's a metal, so it's probably going to form a cation. It's got 2 electrons in its valence shell, so it's probably a +2 charge, and it is. Okay, nitrogen, it's got 5 electrons in its valence shell. It wants 8. It's a non-metal, so it's probably going to add up to get to 8. So it would need 8 minus 5 is 3, so -3. Okay, so I need the smallest whole number ratio in which 2 and 3 are going to cancel each other out. If I cancel the 2, or sorry, if I times the 2 by 3, I get 6. If I times the -3 by 2, I get -6. -6 and 6 are the same, so I'm going to say it is 3 and 2. Okay, there's a shortcut here to make your life easier. You start with your charges, and then we're going to do a little bit of a switch around. This is one of those areas where it works, and mathematically it's just kind of like, huh? But it works. I am going to assume that I'm probably going to need as many nitrogens as the charge is on the magnesium. So I'm going to need 2 nitrogens, and likewise for the magnesium. So nitrogen is -3, take the absolute value, and I'm going to need 3 magnesiums. So I can do the crisscross, and it's going to tell me that I probably have magnesium nitride as Mg3N2, and that is the correct answer. But it does get a little bit funny if you do have the same number on both of them. So let's look at this case, magnesium sulfide, so magnesium and the sulfur. The magnesium, I put the 2 from the magnesium under the sulfur, and the 2 from the sulfur under the magnesium. Now, is that the smallest whole number ratio? No, it's not. That's a 1-to-1 ratio. I don't write it as 2-to-1, so I write it as 1-to-1, and remember, I don't write ones, so it would just be MgS. Okay, is there an easier way to find the charge? You betcha. Okay, so if I look at the periodic table, and I look at my groups, the alkaline metals, group 1, those are all -1. Remember, columns are similar charge or similar chemical properties. One of those properties is charge. Okay, so group 1, those are all going to be a +1. Group 2, those are all +2. Now, over here to this side, I look at group 18, the noble gases. They're all, no, forget it. I'm not being a cation or an anion. I've already got my 8, so they're plus or minus nothing. They don't like to react. The halogens, group 17, all -1. They need 1 more electron to fill up their valence shell. Group 16, those are going to be oxygen, sulfur. Those guys doesn't actually have a name that's commonly used. There are names for it, just not that common. Anyways, these guys, -2. Group 15, nitrogen, phosphorus, arsenic, -3. Carbon's kind of crazy. You can see it +/-4. Usually you see it a -4. It's kind of a weird one. Aluminum, it's like a group, but he's the only one that doesn't make a bunch of exceptions. So aluminum is a +3. So you do 1, 2, skip the middle, 3, 4, then 3, 2, 1, 0. Now why did I skip the middle? Well, that is the d block. The d orbitals are dominating in the middle, as well as, even though they're not d orbitals, the folks down here have the same problems. They're big enough, they have complicated enough electronic shells that they can sometimes have multiple charges. So things like copper comes in 2 possible charges. So you can have two different copper oxides. You can have copper with a 1+ charge and copper with a 2+ charge. They don't even look the same. Classic one is iron. Iron with 2+ charge. You put that with a compound with some salt or some oxygen. That's not the same compound as iron with 3+ charge. Okay, how do I deal with these things? What I call multivalent metals. They're generally the transition metals or the poor metals. Lead does this as well. You have differently charged ions. They're going to have differently charged properties. They're different chemicals. I'm going to have to know what they are. And the scenario is basically going to assume that the name will have it and or I deduce it from the formula. If I don't know the name or the formula, then I'm going to have to experimentally determine it. Now, I'm also going to be assuming that it's an either or, not a both. There's cases where it's both. Magnetite is both. Now, you'll also notice I called it magnetite. That's a geologist name. When it's both, once again, it's getting complicated. You get two different cations. Yo, geologists, deal with it. I'm not dealing with this. Okay, so we got a couple different ways of naming it, and we're going to kind of walk through these here in a bit. The new way is known as the UPAC, International Union of Pure and Applied Chemists. They're basically the ones that get to make up all the rules, although the rules are more like suggestions because, anyways, we're going to be learning these guys. There is an older way of doing this, and in that case, you're going to name the element in Latin. Yeah, there's a reason this is the old way. Unfortunately, it's not the gone way. It's still used. Latin metals, because these are all going to be metals, end in You're going to ditch the and replace it with an ic or an us, depending on the charge. Now, you can also see the difference in the chemical formula. So let's walk through this a little bit. Okay, let's say you're doing iron. Ferrum would be its Latin name. So the old way would be called iron 2+ ferrous, because the us goes with the low one. And iron 3+ goes, it would be the high one, so you get the ic. The old way assumes that you only have two. And that's actually a pretty good assumption. You generally only have two. The new way, the UPAC way, is fairly straightforward. One, we're not going to name it in Latin. We're going to stick with the English name, which is iron. So we're going to call iron iron. Then we're going to give itself a space for the name, because the name has spaces between the terms. The formulas don't, but the names do. We're going to do a parentheses, and then in Roman numerals, we're going to list whatever that charge is. So it's iron 2+. So I'm going to put Roman numeral 2 and then close parentheses. I don't have to memorize which one's iron happens to do. Same story for iron 3+. Yay. I've got iron space 3. So it's iron 3. Makes things fairly straightforward. If I'm looking, once again, at differences, these are different chemicals. So if I had, say, ferric oxide or iron 3 oxide, that's red rust. If I have ferrous oxide or iron 2 oxide, that's the bluing you see on some fine machinery and fine firearms. Very different material. That's your blue steel. Now, copper would be coperium. So copper 2, that's the higher of the two. Note that the higher of the two for copper is the same as the lower for iron. This is based on relative, not absolute. Copper 2+ would be cupric. Copper 1+ would be cuprous. Or the new way, simply call it copper 2 or copper 1, respectively. Same story for lead. By the way, that's also the origin, I believe, of plumbing. You know, good old plumbum. Now, if we've got the chemical formula instead of the name, so we're going the other direction, we're going to sort this out. And once again, this is assuming we're not giving you something like magnetite, which has both. What I want to do is set up basically a question. I know the charge on oxygen because I can look that up on the periodic table, and it only is a -2. But the iron could be a -2 or a -3. So, iron is something, oxygen is something else. I'm going to run some math, do a little bit of algebra. Something times 2 plus -2 times 3, because I know there's 3 oxygens and 2 irons. That's where the 2 and the 3 are coming from. The -2 is coming from the charge of the oxygen. I know the whole thing equals 0. All compounds have a neutral charge. If it doesn't, that's where you get lightning bolts from. So it's not going to have, if it has a charge, it won't have it for long. So the whole compound will have a neutral charge. So I know that equals 0. One equation, one unknown. All I have to do is solve algebraically. I simplify. Something times 2 is 6. Divide both sides by 2. I get question mark equals 3. So I get Fe3, or Fe plus 3, and oxygen minus 2, which is iron 3 oxide, or red rust, or ferric oxide, depending on how you want to call it. Now, of course, you're going to have the bluing on the other side. So let's look at the other case. Once again, iron and oxygen minus 2. Once again, I don't know what the iron is yet, although it's pretty easy to guess. Something plus minus 2 equals nothing. Well, 0. So question mark equals 2. I simply move the 2 to the other side, plus 2 to both sides, good old algebra. And that means it's Fe2 plus. So once again, the plus is sometimes removed, sometimes kept on. Either way you want to run with it. And that's going to be iron 2 oxide, or ferrous oxide. And that's, once again, if you've got some fine machine work or some of the fine firearms, that's the bluing that's on that. Now, so far we've assumed that the atom was simply just one atom making my anion. However, I can have multiple atoms, let's see if I can talk, multiple atoms make up a single ion. These are called polyatomic. Poly meaning many, atomic meaning atoms, and they're ions. In Unit 5, we're going to talk about molecules. Molecules are covalently attached clumps of atoms. Polyatomic ions are molecules that happen to have a charge. So things are going to make a little bit more sense in Unit 5, but I do want to introduce these guys. A lot of them are going to be anions. Actually, I picked one of the few examples that's not with the ammonium. That's the N with the 4 hydrogens around it. Most of them are going to be anions. Most of them are going to contain oxygens. And most of them are going to end with ite or ate. Not all in all of those statements. We're not going to really worry too awful much about naming these guys. There's a lot of patterns to their names. But the general gist is, whatever the name of the polyatomic ion is, that's the name you give. So ammonium is the name of the NH4+. Phosphate is the name of the PO4 3-. So this is going to be, in a compound, ammonium phosphate. Formulas, once again, you're going to do the exact same thing, except for if you have to tell how many polyatomic ions you have to avoid confusion, you're going to put parentheses around it. If you don't, aka it's just one of them, then you don't do the parentheses. So let's look at an example. Ammonium, once again, NH4+, PO4 3- is phosphate, so we would call it ammonium phosphate. And yay, done. If we did a formula, there's only one phosphate, so we don't have to put parentheses around it. We don't put the parentheses where we don't need them. You don't put the 1 if you don't need it. But in order to tell the reader that the 3, this guy right here, belongs to all of this and not just the H, then I have to put parentheses around the ammonium. Otherwise, it would look like it would be NH43. It's not a nitrogen with 43 hydrogens. It's 3 clumps of a nitrogen with 4 hydrogens in each clump. Well, that's salts. We're going to be doing a fair amount of practice in class, so keep in mind, this is something to practice. Get your skills up, writing formulas, naming stuff, etc. But that's basically all we're doing. It's a nice short form. This is a skill you got to practice. And with that, I'll see you in Unit 5.